This meeting is being recorded.
Okay, 2 more minutes and then we go. So we are going to start here in Europe at 2 p.m. or 2:05. And the idea is we finish at 3:30 with the lecture. After 40 minutes, I will let you know, Adrian, so you take 5 minutes break and then another 40 minutes, okay? For the
good.
Total of 1 hour, 30 minutes. And then after Adrian's lecture, most of the organizers or lecturers will be here in case you guys have more questions. And we will repeat that scheme every day. After the lectures, we will take half an hour to attend doubts, questions, etc. Good. So it's now 2:04, so I guess it's 5:34 in India and 20:04 in China. So let's say in 1 minute we go. Adrian, because you were not in the morning, obviously you were sleeping. People are allowed to interrupt you in real time, but raising up their hands.
Yep.
Okay, so you don't need to pay attention. I'll let you know if there is some question. So I don't interrupt you much, you know, but it might happen. And then also at the end, we can take more questions.
Yeah, sure. That sounds good.
Excellent. Well, feel free to start then.
Okay, cool. So good morning, everyone. So I'm Adrian Florio, and today I'm just going to talk about the time evolution and try to explain you, give you some flavor of how, in general, PDEs are evolved, and in particular focusing on the kind of algorithm you use in CosmoLattice. And so it's going to try to be rather pedagogical. The idea will be really to discuss in general how, when you have a coupled set of ordinary differential equation, and in particular discretized PDEs, how, given some initial condition, you can find a solution at some time t that you're interested in. And so this is really like thinking that you have some set of functions z1 to zn, you want to map that to some function z of t at a later time. And this is going to really be the aim of today. And the method of choice to do that is going to be time stepping. So really starting from the initial condition, evolving in time little by little. And the aim of today, we just to go through a bunch of basic example, devising some scheme of how you can really do this time evolution numerically. And then in later lecture, we will gonna apply that to really field theory and really show you how this is implemented through CosmoLattice. So really the aim of today will be to go through really basic examples that are not field theory and see what are the properties of this different algorithm. From example. And the first one will be really a basic and well-known example in classical mechanics, and it's going to be just simply the radial potential. Meaning we're going to consider the case where you have a very massive object, so let's say the sun, and you have some well, let's say the Earth or any of the other planet that is less heavy and that has an elliptical orbit around it. So Kepler problem. And this is going to be a nice example because it has a bunch of basic property that the type of equation that we solve in the end also have. So really 5 minutes to introduce the problem and recall the equation of motion and how this works. So radial potential is really, you just have a potential that depends only on the distance between the two celestial objects. So some coupling constant lambda divided by square root of x squared plus y squared. And now if you take the derivative of this potential, you can find Hamilton equation or Newton's equation if you want, but I'm going to write them in form of Hamilton equation. So you have px dot, which is equal to, of course, minus the derivative of the potential with respect to x. And this simply gives minus lambda x over r. Let me write it quite explicitly. And for future notation later, I'm going to write that k of x and y. Same for the y momenta, minus dv over y, and this is equal to minus lambda y square root of x squared plus y squared. And this is going to be k of y. And then to close the system, of course, you also need to say how the coordinate evolve with respect to the momentum. And of course, they are simply the time derivative of the momenta. Here, note also that I set the mass equal to 1. So maybe sometimes you will be able, but the unit don't match, but actually they do if you insert the mass correctly.
Adrian,
and so this is...
Sorry,
yes?
There is a question, or I saw a hand.
Yeah.
That was by accident. I think that was by accident. I have the feeling. Sorry, I interrupted you. Yeah.
No worries. Okay, so this is a set of basic equation that I'm going to try to solve numerically. Now, it's given some initial velocities and initial velocities and position. How do you evolve that in time? Of course, for this problem, this is not needed, right? Because as you know, there is 4 equations, and in this problem, there are also 4 conserved quantity, and it's integrable, and two-body problem can be solved analytically. In particular, you know that the energy is conserved, so just the sum of the momentum square minus the potential. And also the angular momentum is conserved in this problem. And by using this conservation law, you can find an equation for the radius as a function of the angular momentum, or the position if you want. And of course, I'm not gonna go through it today because it's not the point of the lecture. If you can check on Wikipedia, there is a nice article on Kepler's problem if you don't remember and want to be refreshed. But you can find a solution for this problem. And this is given, it's going to be useful to check that our numerics are correct. It's given by this equation, minus angular momentum square, divided by 1 plus what people normally call E, this eccentricity, as a function of theta. And the eccentricity is given by square root of 1 plus 2 E L square, again in units where the mass is equal to 1.
Sorry, Adrian, to interrupt. So there is finally
Yes.
a comment in the chat. Can you read it by yourself, or shall I read it out for you?
I think I can read it.
If you can address that.
For the dot p, it seems the power in the denominator is wrong. Yeah, sorry. Thank you for that. Of course, it just should be 3/2. Thanks for that. good. So that's our set of equations that are correct now, so it's even better. And so let's try to solve it. And again, so what I was saying before, the most basic way and also the predominant, I'm not saying it's the unique way, but that's normally how it's done. To solve this kind of numerical equation is to do some time stepping. So it means you start from some initial condition and then time step by time step, you try to build solution at a later time. And so the most naive safe things, or the first thing you would try when you look at this equation, probably the first thing that can cross your mind is to simply take the derivative. So say you have any function f df over dt, and then just to try to approximate that by a finite difference in time. So you could say, okay, f of t plus dt minus f of t divided by dt should give some reasonable approximation to my derivative. And then if you do that, then you can just replace that into your set of equations that we had above. Let me use some vectorial form, so I don't need to rewrite all of it in the end. But what you would end up doing is that if you have your momentum at time t plus dt, so this is the solution that you want to look at, then you would say, okay, so this is simply my momentum at times dt, t, sorry. Okay, I see since it's morning and I already screwed up the power in the denominator, I may mix delta t and dt, but so please don't be too confused if I do that. P of t plus simply delta t times this k, which was simply the derivative of the potential that I was writing before. So this k is really the derivative of the potential. I call it k because often we call that kernel, so it's just a notation. K, so evaluated at time t. By that, I really mean that x and y are evaluated at time t. Yeah? And then x of t plus delta t would be x of t plus delta t times p at times t. Okay, and by now I could, well, try to explain what happens if you do that. This is called the Euler method, so it's really probably the simplest algorithm that you can think of, and it was thought of by Euler, so pretty odd. But I think the easiest thing will be just to try it out together and just see what happens, and then we can move on from there. So to that, I'm gonna change the screen I'm sharing, and we're just gonna go together, see what happens. Can you see well, or it looks like it's a bit small, no? Is that okay? Maybe Danny, if you can confirm. Or anyone.
I don't think we see the full screen, just the left hand side.
You don't see the full screen?
No, we see like half side somehow.
Okay.
So before, at first, we could see everything, but you have changed something. No.
Is it better now?
Yeah, now we see, I mean, it's like a fringe, you know, it's not the full screen, but I think we see what you want to show. Time evolution radial
Okay.
potential, no?
Yeah. And is that good enough, or?
I think it's big enough, yeah.
Okay, good. Good. So I just coded this this simple algorithm in Julia, and I'm gonna show you what happens. And then the idea will be basically to build on this algorithm to try to get better and better algorithm and see see just by playing with it what happens. So again, this equation for this Hamiltonian, now the power in the denominator are correct. I just repeat the equation here, and I set up the problem here. So really, I just like wrote in code what I wrote in equation before. I have the potential. I just set the coupling equal to 1. I have the kernels, and I choose some kind of random initial condition. So x equals 0.5, py equals 1. A little function that set this initial condition, maximum time to which I want to evolve, and then also some definition of the conserved quantities, so we can look if they are really conserved or not. And this is just a function to plot the analytical solution. And that's what you get if you try to do this this forward order method that I described before. So really, the algorithm I was talking before, px, py, x, and y are this solution, and really this index I plus 1 or I is the time at which it's evolved. So I start from initial condition p of 0 that are initialized before. And then every time I go to the next solution simply by adding this kernel evaluated at time t, and I do the same for the position. So they are evolved with the momentum evaluated at time t. And you see that if you do that, it really doesn't work, because you know that it's a two-body problem. The orbit that I chose should be stable, and the analytical solution actually it's this little ellipsis here, and you see that the orbit after even one revolution after around the sun, or not even, starts to be unstable and just goes away, showing that this scheme doesn't really work. I mean, you could say maybe I didn't choose dt small enough, so we can try to see what happens if I take a smaller dt, which is here, sorry. So let's say I take a dt 10 times smaller. And you see that now it works better because the time step is smaller, but you see that it still doesn't work. That now maybe you do a full orbit before starting really deviating, but that the algorithm is not stable and maps closed orbit to orbit that are unstable. And this is well, this is kind of a problem, meaning because what we did seemed pretty reasonable, but it doesn't seem to be working. You can see also what happens for the energy. Yes, you know, this is what I'm plotting here, h, the Hamiltonian of just the energy. And this should be a constant, but you see that pretty quickly, basically every time you do a rotation around the sum, you get a huge kick, and the energy is just not conserved. Other plot that is interesting is the px as a function of x, because it's a classical system. This is like a section in the phase space, and it's a stable orbit, so it should be like a closed curve. And you see that really also at the level of the phase space, nothing works. And that's basically what's going to give us some good insight. Also, the angular momentum is really not conserved at all. So like really just doesn't work. So yeah, the question is sort of how can we try to fix that? And this is what I'm gonna try to do now. So I'm gonna move back to my notes. Just seem to have disappeared. So give me 1 second, okay. Sorry, I'm having a little problem with Zoom that is not letting me select the windows I want. Okay, great. So the thing that we just saw is that this specific algorithm doesn't preserve any of the conserved quantity. And in particular, it doesn't conserve angular momentum. Angular momentum. And what I'm going to show you is that if you do a very small modification to this algorithm.
Adrian, I don't see your screen share. I see you're about to share, but I don't know if it's my own problem or it's everyone's problem.
No, I think it's a global problem.
Okay. So let me try to reshare.
Now.
Is that better now?
Now we see the screen.
Okay, great. So yeah, the only thing I wrote is that it does not conserve the angular momentum, so you didn't miss too much. And as I was going to say, I'm just gonna modify what I wrote before, and then we're gonna see that at least angular momentum is gonna be conserved much better. Let me maybe make it clear the vectorial notation I wrote before, just so that we are all on the same page. I'm gonna add this extra notation also, just so that we can go a bit quicker. Any function that is evaluated at t plus dt, I'm gonna write at f plus with a little plus 1. F evaluated at times t will just be f. And then the same for the kernel. If it's evaluated at x of t plus delta t and y of t plus delta t, I'm just going to write that as k plus 1. And I'm also going to use this vectorial notation for the kernel. So given that, I mean, we saw a problem, the angular momentum is not conserved, and so we can try to see just on pen and paper why this is so. And this is pretty easy. We can just compute L plus 1 as a function of, I mean, really in the algorithm. So L plus 1 is simply x plus 1 py plus 1 minus y plus 1 px plus 1. And we have expression both for y plus 1 and px plus 1, so we can just plug them in. So if we do that kind of together, x plus 1 py plus 1 is equal to x py. Now I evolve x, so I have delta t px py. And then I evolve py and I multiply with the x, so I get a delta t ky times x. And then I have a cross product that goes as a delta t square. Delta t square ky px. So now if you plug that in the expression for the angular momentum, what you find is that the angular momentum at time plus 1 is equal to the former angular momentum. So this would be good if it was conserved, but now we will see that we get extra terms. So this term really just comes from this term. So you get x minus py, which was the angular momentum at the time before. Then you have this term that goes like delta t. You see that this one is symmetric in px and py, so just cancels. The only one that seems to survive is the one in kyx minus kxy. But this is also 0 if you look at the form of the kernel that you see here. Because if I multiply this one by y and I multiply this one by x, then you see that they are just the same objects. So if I subtract them, I get 0. So this is also equal to 0, which seems pretty good. But this last term does not cancel. And you still get a variation that goes like delta t square ky px minus kx py. And this is really the term that leads quite explicitly to this violation of angular momentum conservation. But the good thing that we're able to derive some sort of exact expression is that it will allow us to guess a much better algorithm that actually doesn't lead to this explicit violation. And this is, okay, maybe not so easy to guess, but when you know the answer, you can see it pretty easily. If you do exactly the same for the momentum, meaning that you go as p of +1 simply evolution like we did before delta t times k. So you don't change that, but now that you found the solution for the momentum at time t equal +1, you use it to evolve the position. So delta t times p now evaluated at +1. So this +1 here is important. You see that actually, if you do that, you generate an extra term in this conservation of angular momentum. And this extra term really comes from this guy here, which is this px py. Now I have a py that is evaluated, this px is evaluated at +1 also. And you also get an extra term from here, but that we cancel from the other expression, but this extra term does not cancel. And you see that it's precisely equal to, so let me put some quotes to show the new evolution. This extra term is precisely equal to delta t square times kx py minus ky px, ky, sorry, px, which is exactly the inverse of this term. So it seems that if you do this scheme that is called semi-implicit order, meaning instead of just evaluating the next step of x and p together from the previous solution, but really doing sort of a staggered thing, if you want. You first evolve the momentum, and then with the new solution of the momentum, you evolve the position. With this simple modification of the scheme, it seems that you end up with something that should preserve angular momentum. Okay, kind of a wide guess now, and whether this helps or not is not completely clear, but what I'm going to show you is that actually it does help quite a lot. So let me move again. Okay, I just understood something. Sorry. Okay. Okay, next transition is going to be smoother because I just understood why Zoom doesn't like when I do that. Great. So can you see my screen again now, the one with the algorithm?
It's black so far.
Okay, let me try to transition again. Better luck.
Absolutely. Now we see the full screen. Great.
So I also coded this simple modification of the time evolution here that I call this semi-implicit order. It's really what I wrote on paper. Now I start by evolving the velocities or the momentum by also evaluating this kernel at time x, so at time t. And then now that I already computed this solution, I can plug it into the position and use that to evolve my algorithm. And this is what you get here, and you see that it's much better. Of course, at later time, you see that the solution does not exactly match the analytics, but you see that at this closed orbit don't diverge, and they sort of stay. They drift a little bit, but they stay much better. And you see that we're getting somewhere. Now, if I take smaller dt, you will see that now it gets much better, and that actually it seems that if you just like go sort of brute force about it and take smaller dt, you will get very accurate solution. And that's good. Let me put back my sort of larger DT. Or we can also look at this one. This is the conservation of energy. You see that it's not exactly conserved, but at least it's oscillated around some specific value. And I don't think I'm going to discuss it exactly, but what happens here is that the energy is actually conserved, but a discretized version of the energy, and the full energy is just oscillating around this value. And what is even better, and that's what we were trying to achieve by design, is that the angular momentum seems to be exactly conserved. So you see, you start at 0.5, which is the initial value of the angular momentum, and you stay at 0.5. And you stay at 0.5 really up to machine precision. And it's really what stabilized this algorithm here is this intuition that if you can build in conservation law in your algorithm, it's going to help you. I'm also showing here the same phase space as before, and this is now the picture that that you would want to see. Like Px and x form a closed orbit, and this closed orbit is not exact, it's drifting a bit, but what happens is that the area of this closed orbit is always the same, and this is really thanks to this conservation of the angular momentum. And something I'm gonna discuss a bit more later because it's something important for algorithm in general. You also see that the way it behaves as DT, as you go towards smaller DT, energy conservation is better and better, meaning that the oscillation around the conserved value of the energy and the true physical value of the energy, the initial one, is smaller and smaller. And here it seems to be roughly linear in DT, and this is what you would expect by just looking at how you discretize the equation, the errors you do at every time step. And yeah, this is the same plot, but just a violation of energy conservation. So you see here it's at a level of like 1-2%. And this is a better plot that shows that it's really linear. So as a function of dt, this maximum violation of energy is decreased linearly with dt, which is a property of this implicit Euler algorithm. And yeah, so we already see that with this very simple modification that seems to be somehow very very minor and sort of very, that shouldn't affect so much the physics. We went from an algorithm that really doesn't work to an algorithm that seems to be working pretty well. And that gives us already some good lessons that can be learned from there. And so I think that's what I'm gonna go now. It's somehow summarize this this lesson and then see if I have time to continue with the next algorithm or if we take a small break. Let me switch back again. Let's see if what I promise is true or not, and if it gets smoother or not. Can you see my screen?
Not yet.
Okay, so it seems I need to do it twice. So let me do it twice.
Now we do.
Perfect. Okay, so now we know how to do transition. I need to do it twice, and I asked the second time. Great. So and yeah, if you from these lessons, if you already knew the thing, or if you're dozing already, it's the good time to wake up now, because I think it's really the important take home of this last lesson is that, of course, when you do you write down some algorithm, you try to solve some equation. What we want to do is to learn about the physics by solving this equation and like just looking at the solution. And that's why you write down some algorithm to solve this equation. But the other thing that is really important is that you also have an arrow in the other direction, meaning that if you want to write some algorithm that are efficient and that are actually just correct and give you correct solution, it's always helpful to understand the physics of the problem and what are the fundamental symmetries and what are the fundamental laws that govern your problem. And here in particular, what we did is that we built an algorithm that preserves the conservation law, that preserves this symmetry, preserves a conservation law. And in the jargon of Hamiltonian evolution, it's called symplectic. And in particular, it's good for Hamiltonian system. I mean, always when you have symmetries, the more symmetries you can preserve, the better it is. And here also maybe you're wondering why I focus so much on angular momentum and not on energy conservation. And the answer is simple. It's just that if you discretize time, then you break time invariant symmetry. So there is no way to exactly preserve energy conservation simply because you break it explicitly by taking some discrete time step, and there is no way around for that. But of course, once you discretize your system, you don't break rotational invariance, which is what leads to angular momentum conservation. And of course, if you don't break it explicitly, there should be a way to preserve it. And that's what we did by constructing explicitly this semi-implicit earlier method.
Sorry,
just because, I mean,
Adrian, just one
yes?
because in the lattice, we will break to the same level rotational invariance, because we are in a lattice, but you are not here, just to clarify that.
Not for this system, yeah. Not for this system, right? Yeah, I agree. In a lattice, here is just a symmetry of the system, but yeah, I agree. Of course, if you can think in terms of discretizing a field, and here you will break at the level of the lattice the discretic symmetry, but you don't have an equivalent of. You will have other conserved quantity that sometimes we won't want to impose, but really, rotational. This was just a comment for this specific system. Just for the just for the one of you that are interested to go a bit more in detail of what exactly this means. Symplectic and what we achieved here by guessing is a sort of more fundamental structure behind it, is that if you have some Hamiltonian system, so where you have some Hamiltonian function that depends on x and its momentum, or more x, you can put some vector here, and that's also okay. And you have a symplectic structure, meaning that you have some Poisson bracket that are equal to 1. And writing it in this term is also nice because you can, most of the thing that I am explaining now, you can just generalize that to quantum evolution also just by putting Poisson bracket by commutator. So this is kind of an aside, but it's sort of an interesting one. So let me make it. By Poisson bracket, of course, I just mean the usual one. Also, of course, if you don't follow what I'm saying right now, it's just that you have an early break, so it's not so much of a problem, but it's an interesting. I think it's an interesting fact. Px dg over dx. So if you have this structure of that normally is called you have some symplectic dynamics. So you have Hamiltonian Poisson bracket that is equal to 1, and the evolution is just generated by taking the Poisson bracket of the Hamiltonian with a function. So always f dot is equal to the Poisson bracket of h with f. This is called the Hamiltonian flow. Then the fact that it's symplectic just means that it preserves the Poisson bracket. And as a consequence, since conservation law comes from the fact that the Poisson bracket of the Hamiltonian with the conservation is equals to 0, it means that it preserves conservation law. And so, yeah, just kind of an aside, and you see that if you were to do some quantum dynamics, for instance, it would just mean that you found an algorithm that preserved the commutation of the Hamiltonian with everything, and so that it also induces a conservation law. So maybe before we take a break, let me just summarize some algorithm properties in general and set some, just say what properties of algorithm in general, and then we will look at a few other algorithm, and then I'm going to show you how you can apply this idea to actually partial differential equation also, and not simple ordinary differential equation, and that's what we use in CosmoLattice also. So the first property that it's good to be aware of is that you can have explicit algorithm. And this is really what we are going to focus on. And I don't think we're going to ever mention the other type ever after that, but it's good to know that it exists if you want to go in and use your own specific problem that has a different property than what we do. But you also have implicit algorithm. And the only difference is by explicit, I mean that every time you do a time step, you can explicitly solve x plus 1 and p plus 1 as a function of x and p by just writing an equation as I did before. Implicit means that the x plus 1 and p plus 1 depends in a non-trivial way on x plus 1 and p plus 1 also, and you need to solve an implicit algebraic equation at every time step. And why would you do that, you would ask me, because of course this is much cheaper to do and much easier. And the reason is that when you do that, typically, in general, I'm not going to be more precise, that this leads to more stable algorithm. For wave equation like, for equations that are behaved like the wave equation, which is typically what you find in this field theory in expanding background, it's not really relevant because you can explicit algorithm are more than useful. But as soon as you go something different, if you add some dissipation or if you add some diffusion, you go to like equations that are less stable numerically, and normally going to implicit scheme is really a gain and allows you to just solve equation you couldn't with the explicit scheme. So again, it's not going to be useful to use CosmoLattice out of the box, but if you want to think about your own system of equation, it's good to be aware of this property in general. So then you can look it up by yourself. Second thing, maybe just to clarify what I was saying before and what I'm going to say after, it's important to think about order of convergence of the algorithm. By that, I just mean that if you have some exact solution and you're lucky to have some case where you can test, if you know this exact solution and you subtract the numerical solution, you will have something that should be equal to 0, but you have some numerical error, and this numerical error goes to some power of L, and this is the order of convergence of your algorithm. If you're not lucky enough to have an exact solution, and that's most of the time the case when you're beyond the debugging, what you can do also is look at any conserved quantity. And so if you start with an initial value of this conserved quantity, you look as a function of time how it evolves, and this should also go like dt to the power of L. And this is what I was doing before. I was looking at how energy moved, and we saw that it was linear for this case. And the last property I just discussed maybe too much about is that for Hamiltonian system, you can have algorithms that are symplectic, so really preserve exactly. So by exactly, I really mean exactly, like to machine precision, conserved quantities. And what we're going to see after is that you can also have non-symplectic algorithms that work, but that are maybe sometimes less well suited for Hamiltonian system. And I can continue, but I think that's 40 minutes. So
yeah, I think it's fine if we make a break. No, you've been slightly over 40 minutes. So yeah, let's take 5 minutes break. You can also take questions, or I can.
Yeah, of course.
If you want to take a break, feel free to take it.
No, I'm happy to take question.
Very good. So there is a question: will the Julia notebook be posted?
Yeah, I mean, I don't mind at least.
Mm-hmm. We'll put it in Indico, okay? And also some people ask me about the videos. Of course, I'm not sure we're going to be able to upload them right ahead today because I have to figure out what is the best way to pass you that information since the videos are pretty heavy. Maybe we will try to invite some YouTube channel, something like this, okay? But this is to be announced. However, the slides, you have them already in Indico, in the schedule. And this afternoon, we will also upload the slides for tomorrow.
Yeah. Also, the power in the equation is wrong. I should correct that. That's why I wrote it wrong, because I just copied because I was still tired. So there is another question in the chat: is do we have non-Hamiltonian system either? So yeah, I mean most equation that you solve are, I mean, for instance, if you just have a diffusion equation, this is not something you can derive from a Hamiltonian. As soon as you don't have a closed system and you try to take into account dissipation, hydrodynamics, Navier-Stokes equation, or non-Hamiltonian. For what we do in CosmoLattice, or the thing that we have our Hamiltonian system, in the sense they are just derived from an action and they are really from the microscopic theory. So normally they are Hamiltonian. But even in this case, and we're going to see some examples, sometimes you cannot really, at least in an easy way, map that to a Hamiltonian. And this will be the case in the lecture by Ben and Toby on a non-minimal coupled scalar field. And it could also be the case if you try to take into account explicitly, or I mean, rather in an effective way, when you have a decay of particle through perturbative channel, you can do it to some extent. Also, we don't do it. We don't have it in the default version, but this would be a non-Hamiltonian system also. But at the level of OD is like that. The simplest example, I think, is the diffusion equation. So you have some quantity, conserved quantity that now you want to take into explicitly the fact that it diffuses in a thermal bath, and the equation is like dp over dt is equal to Laplacian of p, so partial differential equation, and this is non-Hamiltonian in the sense that I am saying.
Hello.
Hey.
So can you hear me?
We can hear you.
Yeah, I can hear you.
So can we run CosmoLattice with for non-Hamiltonian systems?
Yeah. So so now I'm thinking in the public version, I don't think we released the Runge-Kutta yet, Danny, did we? But it's coming soon, right? So right now, the algorithm that are implemented, they are all symplectic, so they work mostly for Hamiltonian system. But we also have implemented some Runge-Kutta that works out, and I think it's coming out in the next release that should be soon. And yeah, in the meantime, if you really need to do it, you can rather easily code it yourself, the algorithm itself. Can you still hear me?
Yes, we hear you, Adrian. Yes.
Great.
Let me remind, when you want to ask a question with the mic, please raise up your electronic hand first.
And then can you just confirm what I said is correct? We didn't release the Rungekuta yet, right?
You are right. We haven't released that yet. I think we will probably wait for the version 2.0 next year. Although, I mean, there is a possibility we could release the minimal gravitational coupling in Christmas, in which case maybe we release the Rungekuta in that moment. Okay, so well, it's imminent, modulo few months.
Yeah.
So, yeah.
You can probably send us requests also, because if there is a lot of interest, it wouldn't be so hard to release just the Rungekuta without the non-minimal coupling.
Good. I think we can take 1-2 more minutes, and then you are green light.
Sounds good. Okay, since the transition on Zoom are not so smooth, I will try to condense them a little bit.
All right.
I think I can do it with 2 only. So
So for your PDF that is in Indico, they should wait for you to correct this one, Adrian, or that one is still valid to some extent?
no, I mean the only is just this equation of motion for the moment for the.
Okay, it was just that typo in the equation of motion. Nothing.
Yeah.
Well, in any case, we will correct that to put the correct version, no? But
Yeah.
doesn't
But it's not dramatic.
It's dramatic for you to understand, of course, what's the core of the lecture.
Okay, I'm good to go if that works.
I think you can start, Adrian. Go ahead, please.
Yeah, so in the next maybe 15-20 minutes, I'm gonna present a few and play a little bit with the notebook again, higher order algorithm and some that are not symplectic also, because you can use them for other problems. And then in the last 20-15 minutes, I'm just gonna show you quickly how it directly applies to partial differential equation and maybe the one subtlety you need to be aware of in this case. So I'm going to show you how you can construct higher orders algorithm. So meaning by higher orders, I really mean that they converge faster when you take dt that is smaller. And the first version of that are going to be a symplectic family of higher orders that are often called Verlet type algorithm. This is the second order. And if you go see in the review and in the manual for CosmoLattice, you'll have even higher order generalization of that. And the idea is quite smart, is that to realize that you can combine this symplectic step together in a way that cancels errors. And if you combine them with the correct coefficient in the correct way, you can cancel more and more errors. And I'm going to show you that it works with the Julia notebook. So the way you can do that, the first thing you need to realize is that actually the semi-implicit Euler version I discussed before was not unique. You could have done the other way around. The version I talked about was the one where I was saying, okay, let's start with the momentum, and then I evolve them in time. I get p plus 1, and from p plus 1, I can compute x plus 1 maybe a little bit better, because I already know p plus 1, so it's going to give me a better, a more accurate version of p by using this plus 1. But it turns out, and you can redo the derivation yourself also, that angular momentum is also going to be preserved if you do it the other way around, meaning you start with x, you evolve that with the previous version of p, and then you evolve p with the new version of x. So really exactly the same. Delta t plus k now evaluated at +1. And this is another version of the semi-implicit Euler that works well, and that is also order of dt. And the nice realization, and you can compute the order explicitly, but for sake of time and maybe not to bore you too much, I'm just going to show you numerically that it works. If you alternate these two versions, you will end up with an algorithm that is accurate to order of dt square instead of dt. So the idea is that you do half time step and you switch between the two two methods. So one half time step and you alternate between v1 and v2. And you can do that in two ways. You can either start with v1, then v2, then v1, then v2, then v1, then v2, or you can do it the other way around, doing v2, v1, v2, v1, v2, v1. And this gives rise to two different algorithms. The first one is called velocity verlet, VV. And this is literally what I said before. So I first do an evolution of the momentum by half a time step now. P plus 1/2 of delta t k. Then I do x by half a time step. And then, as I said, I swap the version. So I do x by half a time step again. So in the end, what happens is I just evolve x by a full time step using the value of p that I just computed. Sorry, x. X plus delta t times p evaluated at 1/2. And then I finish the evolution of p. So now I am at +1, and this is obtained by p at 1/2 plus delta t 1/2 of delta t times k evaluated at +1, because this is what I computed before. And you can do it the other way around, and this is what is called position verlet. Meaning that you evolve x by half a time step, x plus delta t over 2 times p. Then you do 2 times half a time step for p, p plus delta t times k of 1/2 plus 1/2, sorry. And then you finish the evolution of x. X plus 1/2 plus delta t over 2p of +1. And actually, if you put that together, the claim is that both of this algorithm, velocity verlet and position verlet, are order of dt square, and this is what I'm going to show you in the notebook. But actually, you can go to O of dt n basically by combining the error. If you play the game yourself of showing how this works, you will see that if you do the expansion of this function and you put them together, you basically cancel the errors that go of O of dt. And if you choose this time step appropriately and you combine this step together, you can go to arbitrary order. And actually, in the code, we have some algorithm that go up to O of dt of order 10, which is cool. Is then it's kind of extreme. You really need to have a specialized application where you need exact energy conservation or whatever, but you can really, in principle, do to arbitrary order in N. Also, a note, there is a special version of position verlet that is called a staggered leapfrog, but inside, just saying it because we are also discussing it in the code and in the manual, and it's maybe the most used second order algorithm, but in the end, just wanted to say that it's exactly a position verlet. The only difference is that maybe you already realized, but when you write this algorithm like that, it's a little bit redundant to stop and compute x plus 1, because the next time step will be to evolve by half a time step again. So if you don't want to measure something that depends on x, you don't need to stop at x plus 1. Don't stop. So you really, and the fact that it's called staggered, it means that you always have the position and the momentum at that leaves at different time step if you want. You always have x that leaves at half time step. So you use it, you start by starting at -1 time step, and then half a time step before, sorry. And then you use x that leaves at the integer time step. And then you do the same for p. Here, the only thing that you need to be careful of is that if you want to compute something that depends on x and p, you need to compute it at the same time step. So from time to time, you need to do this extra half a time step evolution to synchronize x and p, and you need to be careful with initial condition also. Synchronize when needed. But this said, let me just show you how this position and velocity verlet worked. I didn't code a specific staggered leapfrog because, as I said, it's exactly the same. So let me move back to the correct window, which is here. So gonna do a first share. Probably you don't see it, so I'm gonna share a second time. Good. No, can you confirm that you see the notebook again?
Not yet, sorry. Now we do.
Okay. Okay, perfect. Oh, I think I was just impatient the other time. So this is this verlet algorithm, velocity verlet and position verlet. So literally what I wrote on the side before, velocity, you evolve the velocity 2 times, that's why it's called velocity. You do half a time step here, so now p x of I plus 1 really contains p of half a time step evolved by half a time step. Then you do a full time step for x, and you finish the evolution of p. And for the position, the reverse. You do half time step evolution of x, full evolution of p, and you finish the evolution of x. And now we can look at our solution. Well, you don't see much of a difference from the other order, except that maybe there is a little bit less of a spread. What is important is what happens when you look at the energy conservation. And so that's really the only difference, is that you see that for these dots that are up there, this is the semi-implicit order in this kind of a greenish color, and it goes like dt. But now, if you look at the position and the velocity verlet, you see that they really go like dt square. And in this case, you see that position verdette, even if the scaling is the same, the absolute violation of energy is a little bit different. But this I cannot say anything because I didn't derive anything. The only thing I told you is that it was going like dt squared. This is also something important in algorithm. Like algorithm that scale this in the same way doesn't mean that they have the same errors in terms of energy, but it really means that they scale in the same way. That if you decrease dt, then the errors is going to decrease by the same power in dt. And yeah, so that's basically what I wanted to say for the symplectic algorithm. The last thing I want to say about this algorithm in general is to present a version of this non-symplectic one, and then I can move on to the wave equation quickly. Let me share the slides again. The other family of algorithm, let me know when you start seeing the screen.
Well, it's again like coming, but not really coming.
Okay, so I'm gonna share again.
Now it's fine.
Great. The other family I just want to talk about is this, and this is because it's really everywhere, and it's probably the algorithm that is used most generically throughout like all different fields, is this Runge-Kutta algorithm that I'm gonna code RK. And here the idea is that you just look at the ordinary differential equation and you just discretize the derivative to as high order as you can directly looking at the equation and just discretizing it consistently to order dt squared, dt4, dt6, or whichever order you want. Right, higher order. Of course, this is a bit simplified what I'm saying. There is a whole mathematical field which is deriving and studying this Runge-Kutta algorithm, but this is basically the idea. And so this is not symplectic, but it works for all our, but works for non-Hamiltonian system. And for instance, yeah, in the typical example that we're gonna see this week is really this non-minimally coupled scalar field. So one such algorithm, and this is the lowest order, Runge-Kutta 2. I mean, it's a whole family. Now, since it's not symplectic, you sort of have more freedom. You can do it in a lot of different ways. But the simplest second order Runge-Kutta 2 that I'm going to show is called modified order, is, as the name suggests, is a other modification of order that is also second order in time, but that is not symplectic. And this is a version where when you evolve x plus 1, you do it like that, delta t over 2, p1 plus p2, and I'm going to write down the expression for this p1 and p2. I'm just using notation that are rather standard and that you can share, that are shared between Runge-Kutta. So if you want to read more about it, you can match with what I was saying. And this coefficient P1 and P2 and K1 and K2. So for P1 is just P, but P2 is a prediction of what the actual P plus 1 is going to be. So it's P plus delta T over K1. And K1 is just K, and K2 is K x plus delta T P, so also prediction of x plus 1, and then just P1. Note that here I change a little bit notation, and I am taking into account that the kernel could in principle also depends on the momenta, because that's what happens in a non-Hamiltonian system, is that now the kernel also depends from momentum, so you cannot derive it from a potential. So that's the second order version of Runge-Kutta, and maybe the one that is the most well-known is the fourth order version of Runge-Kutta, and it's really probably one of the most standard algorithm ever. And it's built in a very similar way, is that you do the evolution of x with some complicated combination of P1, P2, P3, and P4 now, that at each of them is basically a different prediction of what P plus 1 is going to be. And prediction that you can compute only as a function of x and p at the time p equal to 0, but more and more refined. So the compact way of writing it is P1 plus 2 P2 plus 2 P3 plus P4, and P plus 1 is equal to P plus delta T over 6 K1 plus K2 plus K3 plus K4. And these are really just this kernel evaluated in different way. And to be very explicit, let me write P1 is P, P2 is P plus delta T over 2 K1, P3 is P plus delta T over 2 K2, and P4 is P plus delta T times K3. And again, in the same spirit, the Ks are just different different prediction of what K plus 1 should be. So K2 is K x plus delta T over 2 P1, sorry. And K3 is going to be the same, is constructed from this evolution of x plus delta T over 2 P2, 2. And K4 is finally Kx plus delta T P3, P3. And as you can check, all of these different coefficients can be evaluated with x and p at the time t. So it's an explicit algorithm, but it's sort of fancy combination of this different quantity to really extrapolate with O of dt to the 4. And that's the last thing I want to show for this ODE is to see that this algorithm actually work, and even if they are not even if they are not symplectic, you can get some very accurate evolution for a long time before. Eventually, they're going to get unstable because they don't conserve angular momentum, but virtually you can push the time when they get unstable to very, very late time. And then after that, I'm going to show you in the remaining few minutes how this generalize to the wave equation. Can you see the notebook?
Yes.
Great. So this is Runge-Kutta 2. Now let's say that you just trust me because I'm running a little bit late on time that I implemented what I showed you before. you see that the orbit is not diverging, but is kind of worse than the equivalent second order symplectic algorithm, which was this one. So this is kind of to be expected, but contrary to Euler, and simply because the conservation of the laws are the conservation laws are better, it's still kind of okay ish. This is what happened to the angular momentum. So you see that the violation is small, but is growing in time and is there. It's still at the order of 0.3%, which is kind of big, and it grows in time. And this is what eventually gonna make the algorithm break. And same of energy conservation. It doesn't oscillate around the value. It's small, but it grows in time. And for Runge-Kutta 4, you get exactly the same properties. Here I coded the algorithm, same expression that I showed on paper. But now that you see simply by brute force, you get the most precise solution for the same DT. Of course, it takes more computational resources because you need to compute much more quantity, but for the same DT, by eye, it seems it's really hard to distinguish it from the analytical solution. But even if this is the case, you see that the angular momentum, the conservation is at 10 to the minus 7, but this is not my machine precision, is 7 order of magnitude worse than the symplectic one, and also it grows with time. So if you wait very long, eventually this algorithm is going to break, while the symplectic one is still going to be okay. And same thing with the conservation of energy. And this brings me to the end of this different algorithm, and it's a good moment to sort of summarize what I just said. And really what I want to say is that what I was trying to explain is that a typical way to do this time evolution is through time stepping. So meaning that you evolve in time by you really solve the Cauchy problem. You start from some initial surface in time, some solution x of t, x of 0, p of 0, and you go x1, p1 by just advancing in time. So you do this time stepping. The second point I wanted to try to show, and I think what makes it interesting, is that the physics of the problem is important to devise a good algorithm of problem is important. And you need also to think about the accuracy of the solver. And typically, you want to have good conservation of energy, good conservation of your other conservation law, and this is what's going to allow you to have a good and accurate solution. So for the last 10, maybe if I go extra time for 5 minutes, 15 minutes, I'm going to show you how this is actually applied to PDEs. And for that, I'm going to look at a second example, which is the wave equation. The really partial differential equation. And the point, and maybe you're surprised that I spent only 10 minutes of the lecture on that, and it's almost the same. And the reason behind that, maybe you already guessed this, is just that we're going to discretize this PDE in space, and this is just going to give a set of coupled ordinary differential equation. So wave equation in my notation, setting c equal to 1. So the velocity equal to 1. You have some field that depends on x and t. And the wave equation is just a Klein-Gordon equation for a massless field. So it's that, where dt and dx are just the time derivative and the space derivative. And the idea really is that first you discretize it in space, And this was already explained when you introduce a lattice. If you want, in one dimension, 3D x becomes a discrete variable. So see vector 1 and 2, mostly 1. And this means, well, you have some freedom. What is important to think about is that really at this point, discretization in time is not something. You really do whatever you want in space, how much precision you want, if you want, yeah, whatever you want to do. You have a lot of freedom at this point. The thing that we typically do in CosmoLattice is just to use some simple finite difference. So the derivative in space at some point n will just be approximated by some finite difference expression. So n plus 1 t plus phi of n minus 1 t. At this point, really conceptually, at this point, the time variable is still continuous. And t divided by delta x squared.
Just to clarify for everybody, what Adrian is writing right now is the same as the application as forward-backward derivatives that we learned today.
Yeah, exactly. Thanks for the clarification. This is just you use what Danny just said, forward and backward derivative to get the Laplace. And so I'm not saying giving any new information here. Just wanted to make clear that at this point, really, yeah, you do whatever you want to do in space. Here we do this forward-backward finite difference. And then once you did that, you have a system of first-order differential equation, a system of ordinary differential equation. So really, thanks to this discretization of space, you really have a system of a first-order differential equation. And first order because we always keep this evolution of the field and its momentum conjugate. So to get this first order nature, what you do is that you really add this extra equation that dt phi of n and t is some momentum conjugate to phi. And now what you end up with is this system of equation. At every lattice point, you have dt pi n t is equal to the discretized Laplacian of phi of n and t, and dt of phi n t is equal pi of n and t. And so really what you end up with is a system of two n ordinary differential equation, where n is just the number of points on my lattice. So we go from 4 ordinary equation to that we had before xy px py to 2 to 2n, but it's still exactly the same. So you can use exactly the same method. Yes?
Sorry, just for clarity, I think you wrote a different variable for the amplitude of your field. You put phi, like in a scalar field, just to be clear.
Oh, yeah, sorry. Yeah, thank you. This was bad notation. But yeah, in the end, you end up with just this 2n ordinary differential equation, and you can use exactly the same method that I described before. And that's what we're gonna see. I'm gonna move last time to these notebooks, explain you kind of the one crucial difference that you need to keep in mind when you do that, and then gonna come back here to conclude in about 5 minutes. So what we're gonna see is that what I said is sorry, there was just one question in the chat, I see. What do you mean by order of computation? So I don't know if the question is still there.
Finish your lecture and then we address questions.
Okay. Okay, sounds good. Let me share it then. Can you see the screen again?
Yes.
Okay, great. So let's see how it looks like. Now I have this this wave equation. Something I think we discussed before. So you need to choose a boundary condition in space. Here I just took some periodic boundary condition. I coded it in this way. Not important. It's just like a synthetic way of doing it. Is with a vector in Julia. This Circ shift just compute the finite difference periodically, basically. So this is the function that compute first the first derivative in space, forward difference, and then the Laplacian. The forward difference is just to compute some energy. And then initial condition, just start with some Gaussian centered in the center of the lattice. And then I implemented here a position verdette. The way I'm doing it is really, as I said before, I compute the field phi and I evolve it by half a time step. I wrote it again in a concise manner, but it's like really you do it for every point in space and you add half a time step of the momentum. Then I evolve the momentum by one full time step with this kernel that now is this Laplacian of phi. So really at every point in space, I solve this equation. And then I evolve the field phi by half a time step. Here also notes that I always erase the previous solution because when you have this PDE in 1D, you could do it. But if you go to higher dimension, the field themselves start to take some memory. So you cannot save at every time step the solution, but you need to erase it and save it to a file whenever you need. And now if I choose some value for dx and dt, let's say I take both of them to be 0.001, I can solve my system of equation, and then I can plot it. And this is what happens. This is as a function of x. So really, you need to think now that at every point in x, I am solving this couple differential equation, and this depends on the other point in x. And time by time, I evolve this solution. And you see that it works. It works pretty well. Sorry, my computer is kind of old, so it doesn't make solving equation and having zoom up at the same time. But you see that this is basically how the wave equation should work on a circle because of the periodic boundary condition. You have your Gaussian that separates, and then both waves go in opposite direction. And then since it's periodic, they meet again, and you get back the initial condition. And you can also look at the energy conservation, and you see that it's pretty well conserved. There is one thing I didn't mention, but it's really I think the main subtlety that you need to be aware of is that the only difference with ordinary differential equation is that you cannot choose dx and dt in a completely separate manner. And the way I'm going to show you is really sort of by example, but you see now that if I take dt to be slightly smaller, higher than dx, so just slightly bigger than dx, and you do the same, something pretty dramatic is going to happen. So now I have my wave equation, and as I go forward in time, you see that after a few moments in time, you just completely lose the solution. And now the energy just diverges and is 10 to the 230, which is not great. And the reason behind that is really the fact that now that you're solving something in space and time, you need to be able to resolve the velocity at which your information propagates. And here, in this case, for the wave equation in one dimension, the information propagates at the speed of light, and it means that the basically dx over dt needs to be at least the speed of light and not smaller than the speed of light, because if it's smaller than the speed of light, then you don't resolve basically you don't resolve the propagation of information fast enough. And this is what is called the CFL condition, and applies to a partial differential equation when you do this explicit solver, and you do this explicit spatial discretization using finite difference. Also, you need to be basically able to resolve the speed of light, and that's led me basically to my conclusion. I'm gonna go back to the notes and write this down pretty explicitly, and then free you for coffee. So now again, great. So that's the last comments I want to make for this partial differential equation. So the first one, can you see what I'm writing?
Yes, Adrian, yes.
Perfect. So the first one, and this I already made before, the memory usage can be an issue now, simply because you're solving a lot of ordinary differential equation. And here in one dimension, it's really the number of points in your lattice. So it really scales with the volume. In 3 dimension, it would be a 2n cubed. So it really starts to be a lot of different fields, a lot of different variables. If you have more than one field, then it's multiplied by 2 times the number of field also, because you have field and conjugate. So it starts to be very complicated. If you have gravitational wave, it adds even more field. So really, memory can be an issue at some point. Can be an issue. And actually, this also makes using Verlet and Leapfrog type of algorithm good, because you never need more than one copy of the field. Why, for instance, if you do this Runge-Kutta, if you go back and look at how they are computed, you will see that you need to store a lot of copy of the fields to be able to do the computation. Just to be able to do the computation. So if you're limited by memory, you want to think about that. And then the other kind of crucial difference is the CFL condition, is that you cannot, when you have an explicit algorithm, you need to have delta t smaller than 1 over square root of the dimension times delta x. And the square root of the dimension just comes from the fact that when you do finite difference, you can look at what happens along the diagonal of the cube. So this is this is the biggest lattice spacing you need to resolve, basically. And also note that this is another difference, is that the CFA condition actually applies only for explicit algorithm, and so you can in some cases get rid of that and have stable algorithm for every value of dt, also if you go to implicit algorithm, which in some cases can also be useful if you're limited by dt, to keep that in mind, that the CFA condition is really only for explicit algorithm. So if this is a problem, you may think of using some implicit algorithm. But really, this is at least from my perspective, the 2 main difference when you use finite difference, at least, of solving a partial differential equation versus ordinary differential equation. And that's what I wanted to say. So try to explain the time evolution today. And now the next lecture will be to try to apply this idea concretely to field theory and show you what kind of algorithm we use in CosmoLattice. But that's for tomorrow after the first practice session. So yeah, thank you for your attention.
Thank you very much, Adrian. Thanks a lot. Okay, then we are happy now to take some questions if there are.
So there is one in the chat, but I still don't exactly understand what you mean, Mohammed. So I think maybe that's what I wanted to say, whether you discretize in space or in time first, and you ask if this matter. Well, it's not like a subtle thing like order or limit don't commute. It's not like that. It's just the point I like to present it like that you first discretize in space and then in time is simply that when you have different equation, sometimes using finite difference is not the most pertinent thing. Like for instance, if you do very complicated hydro simulation to look at how the flow of airs are on the plane, normally this type of equation, you don't do finite difference, but you do things that are called finite volume or more complicated discretization of space, or sometimes you can use a Fourier scheme, also you solve in Fourier space. And what I wanted to say is that this doesn't matter for doing the time evolution. All these different discretization of space basically are just a way of reducing this like continuous set of equation to a discrete set of equation that you can evolve in time with the algorithm I presented today. But it's not a conceptual thing that you should discretize one versus the other first. I don't know if this answers your question.
While we figure out that, are there any other questions from this last lecture or from the morning lectures? Meanwhile, you think about it, let me tell you that, of course, if you give it a try tomorrow, this afternoon in Europe and tomorrow morning in India and China, if you try to download the code and install it and run it, etc., for basic scenario, this will help you to follow much better the practice session that will be led by Paco tomorrow morning for us. Not mandatory, but it's if you really want to learn how to use CosmoLattice, it would definitely help. Good. If there are no questions, then I think we are gonna close it here. I'm gonna stop the recording.